So we've gone through and we've diligently determined the telegrapher equation solutions and understand how a transmission line, lossless transmission line works, all the mathematics, the 6 fundamental functions there. Then we terminated that transmission line in a load. So we had a terminated transmission line. We examined the ramifications mathematically of this termination by evaluating the boundary condition that z is equal to 0. We also considered one very special case where the load impedance was numerically equal to the characteristic impedance of the transmission line, and the effect of it when we sort of looked at the two-port transmission line as a impedance transformer. If the load impedance is numerically equal to Z0, then the input impedance of the transformation would be equal to Z0 as well. Then we went through and we connected a source directly to the transmission line without the load at the end. And in this case, we viewed the transmission line as a source transformer. We considered the case where the source impedance was numerically equal to Z0, a very important case where the transformed source now retains the same source impedance of Z0. So again, an analogous situation there between the source and the load with respect to this special case. When ZL is equal to Z0, the input impedance is Z0. When ZG is equal to Z0, the transformed output impedance remains at Z0. And of course, both of those things are true regardless of the length of the transmission line. Now we're going to put the whole circuit together. We have a source on one side and a load on the other. And once again, this source is the equivalent circuit for some useful device, or could be a very complex system here. If it's linear time invariant, we can replace it with this Thevenin's equivalent. Likewise, this impedance is an equivalent circuit to perhaps a device, but probably some large and complex system of electrical engineering. And if it's linear time invariant, we can replace the whole thing with its equivalent circuit, its input impedance, and that impedance becomes the load that's attached to our transmission line. So if this does look very academic, why would we simply physically connect this source to this load? The answer is we probably wouldn't. What we do, though, and the reason we analyze this is because both the source here is an equivalent circuit to something useful and important. Likewise, the load is the input impedance to something useful and important. So let's go through and see if we can figure out what is the final answer here now that we've connected our transmission line between a source and a load, between some useful device that is supplying energy and some useful device to which we want that energy to be absorbed. So recall, once we terminate a transmission line in some load, we can determine its load reflection coefficient, just a transformation of ZL into a different representation of essentially the same value there. Once we have a value of gamma L, the load reflection coefficient, then we know the total voltage and total current along our transmission line in terms of that value. So these are the voltage and current of along a transmission line that is terminated in this load. Of course, we look at this and we see that there are unknown constants still there. The complex wave amplitude V0 plus, the complex wave amplitude of the plus going electromagnetic wave propagating in the direction of increasing Z. And of course, we don't know exactly or explicitly what the total voltage or total current is until we determine what this unknown complex constant is. How do we do that? Well, we have a second boundary, and now we have attached something to that boundary. The boundary is at Z is equal to minus L. Let's go ahead and take our results of the first boundary condition analysis at Z is equal to 0 and apply it to our second boundary condition analysis at Z is equal to minus L at the beginning of the transmission line. When we do that, we'll have enough equations where we can solve explicitly for Z's V0 plus, and once we have that, then we will have explicit equations for total voltage and total current. So to do this analysis, again, we have 3 tools in our toolbox. We have our device equations, we have KCL, and we have KVL. First of all, we have 2 devices, essentially, in the circuit analysis. We have a terminated transmission line, a 1-port device, and we have a source, again, a 1-port device. And so we have a voltage and a current for each of these devices at their single port. For the source, we'll call it IN and VN, and if we go through and apply KVL and Ohm's law, we can deduce that this is the equation that describes this source. The VG is simply the voltage drop across this source impedance plus this port voltage Vin, as it's shown here. The second device is a one-port device, a terminated length of transmission line, and the voltage at its single port we can determine by evaluating the equation on the previous page for total voltage of a terminated transmission line. We can evaluate it now at the port plane, in other words, at Z is equal to minus L. So we take that function of position, we insert a value of minus L in there, whatever that happens to be, and we come up with this result. In this case, the only unknown, the only variable really in here is this V0 plus. Do the same thing for current. So we have voltage and current for this one-port device at its port. We have likewise the relationship between voltage and current for this device at this port plane. The only question then is, what's the relationship between the source current and the terminated transmission line current, and the source voltage and the terminated transmission line voltage? And of course, those are easily determined from Kirchhoff's laws. So this part's rather trivial. Again, the current coming out of our source must be equal to the current in this transmission line when evaluated right here at the port plane at Z is equal to minus L. And this is really the only place where students can stub their toe is they might say IN is equal to the line impedance of a terminated transmission line. Well, the line impedance IN might equal to the total current of a terminated transmission line. The total current of a terminated transmission line is a function of position Z. IN is a number. And of course, what we're interested in is the total current at the specific value of position index Z is equal to minus L right here at the port plane. And that gives us then a complex number for that value. So we do that for KCL, likewise similarly for KVL, and we now have two equations. All right, so let's start with our source equation here. And now that we've applied KVL and KCL and the device equation for a terminated transmission line, we can insert things in here. We know the input voltage of our source must be equal to this by KVL and the transmission line equation. The input current by KCL in the transmission line equation must be equal to this, and so we insert that in there. And so we have one equation, and we look here from a standpoint of unknowns. There's really just one unknown, V0 plus, and of course that's what we're trying to determine. Everything else here is a physical description of our circuit or transmission line with both a source and a load connected to it. So we can take this equation and we simply need to solve for V0 plus. Now I say simply, it's not the easiest algebraic operation to do. You may try it. It's somewhat enjoyable, but I'll skip the details there and just jump right down to the answer. When you do the algebra, this is what we get for V0 plus. Now, if we look at it, we see gamma n show up there, and gamma n is just a shorthand to simplify the math expression. It's ugly enough as it is. Gamma n I define as the value of the reflection coefficient function along our transmission line at the port plane Z is equal to minus L, right there at the output of the source or the input of the terminated transmission line. If we evaluated the reflection coefficient there, that is the value gamma n. And of course, if we evaluated the reflection coefficient there by definition of the reflection coefficient function, we would then get, for a terminated line, we would get gamma L times e to the minus j2, remember there's a 2 there, beta L. So sometimes students will say, oh gee, I thought there was a plus sign in the reflection coefficient function for plus j2 beta z, and there is, but of course we inserted minus L into the value z, and that's why the minus sign kind of comes out there. All right, so gamma n that shows up here is really equal to this. Again, I did that to make the math a little bit more compact, but it's still not particularly compact. It's a little bit disappointing, perhaps, that this didn't come out to be a simpler answer. This result, like a lot of results that I show that are, really kind of a mathematical mess of this type, our equations always tell students, that if you're using them to find an answer, you're probably doing the wrong thing. We don't really need to go through, and in this class anyway, and try to slog through here and figure this out, what the value of V0 is, so we can insert it back into our telegrapher equations and find total voltage and total current. Rather, we do all this to get some insight as to what's going on inside of our circuit or inside of our transmission line. And of course, that's the most important thing with all of our mathematical results. It's not the math is not a template for how to punch the buttons on our calculator. The math is a description of physically what's going on. It's the language that describes it. And so we need to look closely and see if we can ascertain anything interesting about what's happening along our transmission line. So the one thing to take away from this result that's crucial in our understanding of transmission lines and how they work is that this value V plus, and remember that is the complex wave amplitude describing the plus going wave, the electromagnetic wave that is propagating from the source to the load. The complex wave amplitude that describes the wave propagating from the source to the load, of course, depends on the source itself. We would certainly expect that to be the case. But if we look closely, we also find that the complex wave amplitude describing the wave propagating from the source down to the load, that complex wave amplitude also depends on gamma n, which depends on gamma L. Gamma L is the load reflection coefficient. In other words, the load at the other end of the line has something to do with the wave that is propagating from the source to that load at the other end of the line. And this causes confusion with students. It seems to defy causality. Certainly the plus wave from the source toward the load should depend on the source. It should depend on the transmission line, Z0, that it's propagated along. But why would it depend? Why would why would the impedance of the load itself have any effect on the wave propagating from the source down toward that load? So the problem here is that students oftentimes try to assign causality to that plus going wave, that the source itself is uniquely and independently determines the plus going wave down the transmission line. And certainly the source makes a difference. If we have no source at the beginning of our transmission line, then we have no plus wave at all. We have no energy or current or voltage anywhere. But as we just showed, the plus wave propagating from the source to the load depends on the value of the load impedance at the other end. And this really, again, eliminates this idea that we should sort of say the source is the cause of the plus wave and the source alone is the cause then of the plus wave. We can't make it a cause and effect. There is a typical thought among students that the plus wave is something that's sort of emitted from the source. The source injects the plus wave propagating down the transmission line. It's completely due to the plus wave. The plus wave gets down to the end where the load is, and then there's this reflection that occurs, this bounce, and it bounces off the load and back toward the source. And in many ways, that is a correct interpretation. Students oftentimes kind of get this idea because they've seen bounce diagrams in some of their course where there is a transient on the end of a transmission line, and we can follow the transient as it propagates down the line and hits the load at the end and bounces off and turns around and propagates back the other way. And so we start to assign causality. The source creates an incident wave toward the load causes reflected within that comes back. The key thing, though, in time harmonic analysis is our sine waves have been on forever and will be on forever. In other words, this is a steady state analysis. All the bouncing has been done. If we were to go through and look at our transmission line at the moment that our sinusoidal source turns on, then we would see that there would be no energy or current in our transmission line, and then we would see energy propagating down from the source to the load. And when we get to the load, it would reflect, and we have energy that would go back the other way. But when it gets back to the original source, it reflects again and goes back down the transmission line for a second time. And then it bounces back and forth a third time and a fourth time and a fifth time. And of course, when we have a source that's on forever, this time harmonic source that's on forever, what we're seeing is a superposition of all those bounces. We have a situation where all of them essentially are being included. Part of the incident wave is due to the source energy coming down for the first time, but also part of it could be due to the second time around reflection. It's from the source to the load, back to the source, back to the load, toward the load again. And of course, that second time around will depend on the value of the load impedance. Likewise, the third time around, the fourth time around, the fifth time around, they're all components in that total wave. So you have a situation, because the bouncing back and forth, there is really no start and there's no finish when we talk about a time harmonics system that has been on forever and will be on forever. It's no more logical to say the plus wave creates the minus wave than to say the minus wave creates the plus wave. What we have is a situation where both waves must exist in the steady state, such that the boundary conditions simultaneously on either end of the transmission line exist, are validated, are correct for those situations. Again, one doesn't cause the other. They both have to simultaneously exist. Now, having said all that about we can't establish causality, the source does not create the plus going wave any more than the load creates the plus going wave. We can establish causality, though, for one specific case, one special case. And of course, we've seen this case before. This is the case of the quote-unquote matched source, where the source impedance is numerically equal to the characteristic impedance of the transmission line. What we'll see in that case, the plus wave, the wave propagating from the source to the load, is dependent completely on the source, and therefore it is, in other words, completely independent of the load impedance at the other end. So to show this, let's consider our complex wave amplitude V0 plus under the condition now that the source is a quote matched source. The source impedance is numerically equal to Z0. So we go in here, and here's our general solution for the complex wave amplitude V0 plus. We see ZG occurs one time right there, and we set it a value that is equal to Z0, a matched source, in other words. We can simplify our algebra a little bit there. Notice we have gamma n. Gamma n depends on the load impedance, and this could be anything, all right? We don't know, there's nothing special about the load that we're doing at this point, just the source itself. But we notice that we have gamma n minus gamma n, and so we analyze this whole denominator, and we simply get a value of 2. And so V0 plus, the complex wave amplitude of the plus going wave, reduces to this. And the most important thing about this is gamma n is nowhere to be seen. Gamma L, therefore, has no effect. The load has no effect on the value of V0 plus. In other words, the load has no effect on that plus going wave. For a matched source, we can determine the plus going wave explicitly without having to know what's attached to the other end of the line. For a matched source, we can say the plus going wave is completely causal with respect to the source. The source creates that plus going wave. So for this special case where we have a matched source, the plus wave voltage we can consider as being the source wave. Again, generally speaking, we can't. We just have a plus wave, which is dependent on both the source and the load. But for a matched source, quote-unquote matched source, where ZG is equal to Z0, we can say V plus is due specifically to the source. We can calculate what that plus voltage is. We know the value of V0 plus. We insert it into our solution for the plus wave voltage, and this is the result. This is the result of the plus going voltage for a transmission line with a matched source connected to it. Again, this is independent. We don't care what's connected to the other end of the transmission line. We don't care what the load impedance is. And so then we can say that the minus wave is a causal result of this stimulus, of this incident wave. The source creates the plus wave, it propagates down to the load. When it interacts with the load, then it creates a minus wave. We have a sequence of causality that can be established if we have a matched source. Now, the question you might be asking yourselves is, what about the, the second time around and third time around? What happens to the, I thought part of the wave coming from the source was due to energy that had propagated back and forth between source and the load multiple times. Well, that's really the reason that the matched source, it becomes one where the plus wave is causal with respect to the source. The reason that we don't have multiple time around, that we don't have to worry about that, is it turns out if the source impedance is numerically equal to Z0, there is no second bounce. There is no bounce from the source itself. So a wave propagates down to from the source down to the load, reflects off the load, goes back to the source, and that's the end of it. There is no second reflection if the source impedance is numerically equal to Z0. If it's not, if it's something else, then we will get another reflection off the source, and a second time, a third time, a fourth time. We have a summation that would add together to find the total steady state result. All that math where we do the summation, the infamous summation in the case where we have multiple reflections, we do in ECS 723, but we're not going to do that in this class. Also in ECS 723, we can see that when we have a matched source, our infinite summations of multiple time around bounces and propagations reduces to a single simple term, one that is attributable to the matched source and the matched source alone.